Astonishing things that we would never have envisioned will be uncovered to us. Is this the sort of group where everything appears possible? We will find mind-boggling things that we won't ever envision. Furthermore, isn't that normal of this group, where the unimaginable becomes conceivable? Individuals have frequently addressed whether they are the only species in the wide universe. We have investigated the chance of life beyond our little blue planet, gazed at the sky, and contemplated far-off universes. Finally, that chance has appeared. The head of NASA recently said that something wonderful has been caught by the James Webb Space Telescope, our window to the universe. Plan yourself, as an extraordinary mystery has been uncovered on the edges of our inestimable area. The discovery of life in the world Proxima B. It modifies everything. Show up as we investigate the secrets uncovered by the James Webb Space Telescope and conjecture on the potential ramifications of the finding of life on Proxima B for both mankind as a whole and space exploration overall. A scientific wonder, the James Webb Space Telescope has the potential to totally change how we might interpret the universe. Because of the telescope's trend-setting innovation and exceptional area in space, researchers can now study far-off universes, planets, and stars in a way that has never been possible, giving them an unmatched perspective of the universe. Albeit all of this seems like a lot of cheesy declarations, the innovation really upholds all of that. The 6.5-meter diameter primary mirror of the JWST is one of its most astonishing highlights. This is over 2 times as huge as the primary mirror on the Hubble Space Telescope, quite possibly one of the most significant space exploration instruments of the most recent 30 years. The JWST's huge mirror permits it to get, indeed, even the littlest light gleams from the farthest reaches of the universe, regions that science hasn't forever been able to notice. Hence, for most of time, science researchers have just made speculations about what is feasible to see using a traditional telescope. Anyway, with this one, they can finally see the real detail of which they had been fantasizing. The JWST has a major mirror in addition to an assortment of cutting-edge instruments that can detect a wide range of light frequencies. The telescope's near-infrared camera, or NIR-CAM as it's usually known, is a powerful instrument made to take pictures in the near-infrared part of the electromagnetic range. Why does this matter? Well, we can go farther into the depths of the universe because near-infrared light can go through dust mists that block out visible light. Stargazers can see the introduction of stars and systems very close because of NIRCam's high-resolution imaging capacities. The principal objectives of this particular gear are to investigate the early universe and its initial light, explore the beginning and development of galaxies, and find and describe exoplanets previously inaccessible by telescopes. Hidden complexities and designs are uncovered in the detailed photographs taken by NIR-CAM. Grasping the gathering and advancement of galaxies over the course of time is helped by this, and it gives insights into the multifaceted cycles that form our local neighborhood and beyond. Anyway, that is just one instrument. The near-infrared spectrograph, NIR-SPEC, is another option. Through the most common way of analyzing the light produced by cosmic objects into its constituent tones or frequencies, it increases current standards for the investigation of stars and galaxies. This methodology, known as spectroscopy, gives significant insights about the temperature, speed, and chemical composition of these objects. NIR-SPEC provides researchers with detailed data about everything it takes a gander at, thanks to its ability to study the spectral marks of stars and galaxies. By investigating the spectra's absorption and emission lines, researchers can identify the parts of a star or galaxy and dive deeper into the materials that make up the universe. This information helps in our understanding of the complex interactions that happen among stars and galaxies, as well as the life patterns of these heavenly bodies. Moreover, NIR-SPEC is fundamental for concentrating on distant, high-redshift galaxies. These universes give forward light that has come to us after traveling billions of years, giving us a glimpse into the early universe. Stargazers may decide a galaxy's age, chemical composition, and other properties by examining its spectrum, which gives insight into the system's entire developmental history throughout cosmic history. The mid-infrared instrument, MIRI, on the JWST is the primary instrument for exploring the mid-infrared part of the electromagnetic spectrum. With MIRI, we can concentrate on objects that produce infrared light at longer frequencies, which allows us to investigate different phenomena, ranging from star formation to the discovery of exoplanet climates. Asking into the dusty conditions where stars are made is one of MIRI's primary goals. These thick dust clouds are penetrable to infrared radiation, which enables MIRI to glance through the astronomical shroud and notice the development of stars and planetary systems. Space experts may get familiar with an extraordinary arrangement about the actual processes occurring inside the heavenly hatcheries, thanks to the detailed photographs and spectra it takes in the mid-infrared. That is not all, though. In addition, MIRI is essential to the identification and investigation of exoplanets. To enable the identification and inspection of the weak warm outflows from exoplanet environments, it achieves this by making mid-infrared perceptions. The composition, temperature, and movement of exoplanets, as well as their possible habitability, might be studied thanks to this ability. We can identify the presence of water vapor, carbon dioxide, and other essential chemicals, thanks to MIRI's discoveries, which might highlight the requirements for life as we know it. Anyway, those are simply elements that could sustain life. How does the James Webb Space Telescope search for organic markers? Spectroscopy and air examination, which utilize the four instruments we just talked about, are two of its essential techniques. You see, a planet might not have had plants or oxygen all along. Indeed, even while those show life to us, science doesn't trust that to be the groundwork of life on a planet. In this manner, the telescope needs to be incredibly precise. Spectroscopy, a strategy that allows researchers to look at light produced or consumed by an object to learn its composition, is at the center of this technique. Spectroscopy assumes a critical part in uncovering the atomic secrets hidden in the airs of exoplanets. When the JWST finds an exoplanet, it anticipates a transit event, which is a celestial show in which the exoplanet appears to us as it passes before its home star. During this transit, the JWST closely monitors the starlight passing through the planet's atmosphere with its best-in-class instruments. The JWST records this precious light while MIRI rules the mid-infrared range and NIRSpec focuses on the near-infrared. When combined, they make a superb team that can cover an expansive assortment of frequencies required for top-to-bottom analysis. JWST begins its meticulous investigation of the light it has seen by investigating the absorption or emission lines in the light spectrum. Researchers can use the telescope's spectroscopic abilities to pinpoint specific compounds that are present in the exoplanet's atmosphere. Since each molecule has a different arrangement of spectral attributes, no two atoms will be the same. To carry the whole story to a single, understandable page, they basically have to be analyzed and gathered to obtain exact discoveries. The JWST does thorough modeling and adjustment. It matches the observed spectrum features with their corresponding chemical identities using complex virtual simulations and reference spectra of known substances. Think of it as cross-referencing a cosmic dictionary to understand the atmospheric language of the exoplanet. Anyway, identifying specific compounds is just the most vital phase in the search for life. A more complete, comprehensive technique is required. Analysts search for molecules that are viewed as biomarkers or compounds that may be associated with life as we know it. As we've mentioned previously, these biomarkers may consist of gases that are vital for life on Earth to exist, such as oxygen, methane, and water vapor. All things considered, more data and observations are required to assess the general habitability and any significant biological activity markers. Near spectroscopy is another instrument that the JWST uses to improve its search for life. To draw significant correlations, researchers look at a couple of exoplanets with comparable properties instead of a huge number of isolated exoplanets. Finding repeating patterns or variations in the observed spectra of different exoplanets is the objective of comparative spectroscopy. Looking at a range of exoplanets, some of which might be habitable while others may not, allows us to search for examples or anomalies that could reveal insight into the presence of molecules or processes pertinent to life. The JWST looks for exoplanets that are equivalent to one another in terms of size, mass, distance from their host star, and other relevant factors. Altogether, to do comparative spectroscopy, scientists can isolate out the effects of various atmospheric components and focus on possible habitability markers. Researchers can look for similarities or differences in the identified chemical absorption or emission lines by comparing the spectral data gathered from these target exoplanets. It could be an indication that essential parts of life, such as oxygen, methane, or water vapor, are present on potentially habitable exoplanets if specific molecules or patterns are routinely seen in their spectra. The context that the research procedure offers is very helpful in grasping the spectroscopic data. It enables scientists to distinguish between attributes that are likely to be connected to life and those that could be attributed to non-biological phenomena like volcanic activity or atmospheric chemistry. This is due to the fact that, despite appearing to be restricted to Earth phenomena, such as volcanic activity, it actually occurs across space. Despite the fact that some planets are likely inhospitable, they still experience incredibly high levels of volcanic activity. Moreover, researchers could track down anomalies or unforeseen variations in the spectra using similar spectroscopy. These deviations could address particular elements of a specific exoplanet, suggesting the presence of unique environmental conditions or maybe alien life forms that go against existing hypotheses. It's like finding astronomical surprises and going beyond the domain of what we previously believed was possible. A more complete understanding of the habitability of exoplanets, generally speaking, is also provided by near spectroscopy. Researchers can get familiar with the different aspects that lead to habitability by studying a wide range of exoplanets. It helps with our perception of the essentials for the origin and sustainment of life in different cosmic settings. According to the NASA boss Proxima B, which is as it were 4.24 light-years far off from our solar system, has gained significant attention due to its possible habitability. Life might have been found there by the James Webb Space Telescope. Proxima B orbits Proxima Centauri, the parent star of Proxima B, a red dwarf that is still substantially smaller and colder than our Sun. This exoplanet was discovered in 2016 and is located in the Goldilocks zone, the star's habitable zone. The region surrounding a star, known as the habitable zone, is where conditions would be ideal for liquid water to exist on a planet's surface, which is essential for life as we know it. The discovery of life on Proxima B is revolutionary due to its proximity to Earth and position in the habitable zone. Proxima B's potential to support life has generated a lot of attention and speculation. It's important to remember that an exoplanet's habitability is a complex puzzle with many factors to consider. With a mass of around 1.3 times that of Earth, Proxima B is classified as an exoplanet similar to Earth. It takes about 11.2 Earth days to complete one orbit around Proxima Centauri, according to its orbital period. However, things are more complicated than they appear at first. It doesn't follow that the planet will be an identical copy of Earth, and that anyone can easily move there, because it orbits a red dwarf star and is roughly the size of Earth. There are different criteria that determine Proxima B's habitability. The planet's atmosphere is one significant factor in addition to acting as a barrier against harmful radiation. Climates are essential for maintaining life and controlling temperature. Still, the exact composition of Proxima B's atmosphere is unclear, which makes it challenging to make a firm determination about its habitability. Scientists are using the James Webb Space Telescope, among other instruments, to explore Proxima B's atmosphere. They will be able to examine the light that travels through the exoplanet's atmosphere. By analyzing the spectral fingerprints, researchers can look for compounds that may be biomarkers, marks that highlight the presence of life. The presence of water is another aspect that impacts habitability. Proxima B is in the habitable zone, but whether it has enough water on it to qualify as a planet suitable for life has yet to be determined. One significant part of the riddle is water. Whether it takes the shape of lakes, rivers, or seas, researchers search for evidence of liquid water on the planet's surface because the presence of water is necessary to sustain biological processes and is often considered a key indicator of habitability. They also consider the presence of water in other states, such as ice or vapor. Proxima B's tidal-locked state also raises concerns about its possible habitability and atmosphere. To determine if Proxima B's temperature is suitable for supporting life, researchers must also investigate factors like pressure, temperature, and geological activity. Life can be challenging under extreme environmental conditions like intense heat or freezing cold. Moreover, stability is crucial. as habitability may be disrupted by frequent seismic activity or volcanic eruptions.